Here's number 4. Okay, function f is defined on the closed interval from -2 to 8, satisfies order pair 2, 1. F prime is given. We have a semicircle and 2 line segments. Does f have a relative minimum, relative max? Give reasons for our answer. Well, if we're looking at our f prime graph, we'd like to kind of label what we're looking at here. So anything above the x-axis, this is again f prime graph, means my original f graph is increasing. Anything below the x-axis means my original graph is decreasing. Okay, so this is negative slope. Anything on the x-axis is where the original graph is experiencing slope 0. Okay, so here's my f prime sign line. X-intercepts -1, 2, and 6. I'm just going to look at where the graph is located, whether it's above or below the x-axis. So we're starting above the x-axis, positive slope. Between -1 and 2, below the x-axis, negative slope. Between 2 and 6, above the x-axis, positive slope. And then between 6 and 8, also positive slope, or above the x-axis. Okay, so we see that at x equals 6, there's neither a relative max nor relative min, because our original graph is going to be rising, flattening out, and rising again. So there's no relative. Yeah, we have neither relative max or min at x equals 6. Okay, so that's part A. Part B, on what interval is the graph concave down? I'm just going to get this out of the way here. So concave down is looking at the second derivative, information about the second derivative based off the f prime graph. So endpoints will stay the same. And now we're going to look at the peaks and valleys, because we know the peaks and valleys of our f prime graph is going to translate to the points of inflection of the original graph. So we know there's a point of inflection at 0, at 4, and at 6. We would not, well, we would include -2 and 8 as endpoints, but it would not be a relative max if it's an endpoint. Right, so endpoints are not, it can be an absolute max or absolute min, but it can't be a relative max, relative min. Okay. So then once we identify our peaks and valleys, then we look at the slope, because the slope of our f prime graph will translate to the concavity of the original graph. So negative slope means that my slope is becoming more negative, which means concave down. Between 0 and 4, a positive slope on the f prime graph will translate to concave up. Between 4 and 6, negative slope, concave down. And then between 6 and 8, positive slope, concave up. So we can see that the graph, our original graph, is concave down from -2 to 0, and then from 6 to 8. Sorry, down, up, down, up. Okay, -2 to 0, and then from 4 to 6. Sorry, -2 to 0 and 4 to 6. Okay, go with A and B. Okay, part C, find the value of the limit or show that it does not exist. So I'm thinking that this is probably going to be L'Hopital's rule, just because of the messiness that I see, but we always want to confirm it. We don't want to we never want to jump to conclusion without first confirming what's happening. So first thing we always do is we have to evaluate the limit. So replace every x with 2. See what results we get. before we decide what to do next. So 2 inserts itself for all the x values. So I get 6 times f of 2 minus 3 times 2 all over 2 squared minus 5 times 2 plus 6. F of 2, they tell us what f of 2 is at the very beginning of the problem. F of 2 is equal to 1. So I get 6 minus 6 is 0, 4 minus 10 plus 6, 0. Okay, so now this gives us our green light for us to do L'Hopital's rule. Again, this is what AP exam, they're going to take off points if you use equal signs. So just make sure you use arrows along the path, along the way for your L'Hopital's rule. Okay, so we're going to get 0 over 0. We can do L'Hopital's rule now. Again, the purpose of L'Hopital's rule is to create a different version of the expression so that we can find the limit and get a real number out of it. Because right now the whole is kind of blocking the view of what the true limit is. But we do know there's a limit existing. It's just getting hindered by that 0 over 0. Okay, so let's find the derivative. 6f of x becomes x times f prime. 3x becomes 3. And then denominator, we get 2x minus 5 plus 0. So now that we have another version of the expression, we can continue to evaluate our limit. And the hope is that through L'Hopital rule, that we can actually arrive at a real number for our limit instead of 0 over 0. F prime of 2, because f prime of 2 is based off of this graph now. So f prime of 2 is the y value.
Oh, okay.
Because this is the f prime graph.
Okay, yeah, sorry.
Yeah. Mm-hmm. Got it, yeah. Okay.
And then when it says justify your answers after showing your work, or they want an explanation.
Find the value, show that exists, justify your answer. Yeah, so justify your answer is show that we're getting indeterminate form and that we're applying L'Hopital's rule, and then that we're reevaluating and we're getting to this. Okay. Yeah, so we don't have to write any justification in terms of words. Yeah. Part D, find the absolute minimum value. So anytime we see the word absolute max, absolute min, that should remind us to apply extreme value theorem, so EVT. So extreme value theorem, we're going to pick out our candidates from our F prime sign line. Don't look at the F double prime. So we know we're going to test -2 and 8. We know we're going to test a -2 because of relative min. But there's no need to test -1 because we know -1 is a candidate for absolute max, but it has no chance of being absolute min. And we can also skip over 6 as well. So we can just test -2, 2, and 8. So we're going to apply extreme value theorem. We're going to test -2, 2, and 8. And the formula that we're going to use, because they don't give us a formula to find a value off the F prime graph, sometimes they will give you a formula like this, the integral from, 0 to x of F prime at dx equals g of x. Sometimes they'll give you that formula. In this case, they don't give it to you. So if they don't give it to you, then we have to use our adapted formula, final equals initial plus displacement. So we do have an anchor point. Our anchor point is f of 2. So we're going to find f of -2. We're going to find f of 2. We're going to find f of 8. And then we're going to be accumulating the area between the graph and the x-axis. Okay, so Yeah, on my key, or yeah, I put part D on the separate page just because of all the work that we had to kind of get to. Okay, so I'm going to go to the graph now and find all those areas that I need to get to my all those endpoints. So I see a bunch of triangles and I see a semicircle involved here as well. So I'm just going to fill out information for my graph here. I have a triangle here, 1/2 base times height. That's a displacement of 1. This triangle here is below the x-axis, 1/2 base times height, displacement of -2. This is a triangle here, 1/2 base times height. And then here, this is not itself a geometric shape, but we can think of it as taking a rectangle, subtracting a semicircle, and then the resulting portion is these kind of curved subregions, right? So if we think of this as, oh, this is a rectangle with a width and height of 8, and then this is a semicircle with a radius of 2, and we can do 1/2 pi r squared, and that gives us 8 minus 2 pi. So 8 minus 2 pi are these shaded regions from 4 to 8. Okay, so I want to find f of -2 first. So f of -2, I have an anchor point at 2, so I'm going to start at 2, and I'm going to end up at -2. So we're going backwards, but we have to kind of follow what the formula says. The formula says that if we're starting, whatever point we start at, that make sure your lower bound matches your starting point, and then your ending bound matches wherever you want to end up. So I want to go from 2 to -2, but now that I have it on paper, I realize that I prefer my bounds to be in the order from left to right. So I'm going to take the time to swap the bounds, but then adjust that swap by pulling a negative out in front. So f of 2 is 1, we know, and then the region, the area from -2 to 2 is going to be these two triangles here. So it's 1 minus 2. Right. This region is also an area of 1 here. So I split this triangle up into 2 right triangles here. So 1, -1, and -2, which gives me -2. So my f of -2 is 3. That is my endpoint's location. F of 2 is 1. That's given to me, so I don't have to do any work there. And then lastly, I need to find f of 8. So f of 8 is f of 2 plus the region from 2 to 8 under f prime. So from 2 to 8, it's the triangle plus this subregion here. So 2 plus 8 minus 2 pi. This is without a calculator, so we do need to do a little bit of approximation on our own. Just think of pi as 6. Sorry, think of pi as 3. So 2 times 3 is 6. We know this is around 5-ish. And between 5, 1, and 3, we see that our lowest y value is 1. So this is going to win out. This is going to be our absolute minimum. So by EVT, since our function is continuous, we don't have to say anything about differentiable, but because the problem tells us the function is differentiable, we can therefore conclude that it must be continuous to begin with. And then our absolute minimum value is 1 at x equals 2. Sometimes they call EVT the candidates test because we're testing different candidates, but we don't have to necessarily say that. Just have to show the work. Show that we are testing our candidates and that we are making the appropriate conclusion to find the absolute minimum. Okay, next up, number 5. Function f and g are differentiable. Twice differentiable, that just means a smooth curve. Table shows values of the function and their first derivatives as selected values of x. Let H be defined by H of X equals F of G of X. Find H prime of 7. We need to be able to look at this and recognize, okay, this is not product rule. This is chain rule because G is inside the F function. If I want to find H prime, I need to step through chain rule. So chain rule says outside derivative times inside derivative. So H prime is F prime of G of X times G prime. So the outside portion is F. So I take outside derivative times inside derivative. Okay, once I have my chain rule built, replace every X with 7. And then now I just need to carefully substitute portions one by one until all of our function notation is gone. And then we're left with just a numeric value. So once I'm here, I see that, F prime of G of X is, we don't want to be able to do, it's hard to do this all in one step. We have to kind of take a step by step here. So let's look at that G of 7 first. That G of 7 we can find by the table. So we go to our G function table. G of 7 is 0. So we'll replace G of 7 with 0. And then that allows us to look at that outer portion a little better. We're left with F prime of 0 and G prime of 7. So F prime of 0. We look at our table. It's going to be 3/2. We look at our table for G prime of 7. G prime of 7 is 8. And then now that we're down to numeric values, we can calculate and get an answer. Okay, part B. Let K be a differentiable function such that K prime equals F of X quantity squared times G of X. Is the graph concave up or concave down? So we know to get to concavity, we have to get to the second derivative. So second derivative, we have to go through product and chain rule. That F of X squared is a hidden chain rule there. So let's step through. Let's understand that product rule is going to be the larger rule. We're going to apply that first.
If you were to do chain first, would you still get the same answer?
Yeah, we don't want to do chain rule first. Now we would do chain rule first if for some reason it looked like this. If it was like, F of X plus G of X quantity Q, something like that. If your exponent is outside the entire function, then you'll do chain rule first. Yeah, so you always want to see what rule impacts more of the problem. Whatever has a larger impact or wider impact, that's what you want to apply first. Okay, good. So product rule has a larger reach, so we're going to apply product rule first. So F prime G plus FG prime, I laid everything out. Now to get to F prime, this is where we have to go through chain rule just for the F portion. So outside derivative, we do 2 bracket to the first power times the inside derivative. All that is where the chain rule is going to occur. And then G of X, we stay the same. F of X squared, we stay the same. And G prime is just a derivative of the second expression. Okay, that's the hard part. The hard part is just building out that derivative, because from here, you're just replacing every X with 4 and then using the table to get it down to a number. Okay, so we do that. Replace every X with 4. F of 4 is 4, F prime of 4 is 3, G of 4 is -3, F of 4 is 4. We have to square that. Now, the whole purpose is not only to find the second derivative value, but then to determine whether it's concave up or concave down. So -72 plus 32, we get -40. A negative value for a second derivative function is going to indicate concave down. So that's our conclusion. Part D, is the function defined in part C increasing, decreasing, or neither at x equals 2? I'm sorry, I needed part C. Sorry, part C. Let m be the function defined by m of x. Find m of 2. So m of 2, I'm just going to replace my x with 2 and then just have to accumulate the area under the f prime graph. Well, I don't have the f prime graph, but I can apply first theorem. But first, I'm going to set everything up. So I'm just plugging into my formula here. So I'm just replacing all the x's with 2's. Now I don't have a graph for me to read the area under the f prime graph, but we do have f of x available. So what we can do is we can use first theorem. So first theorem says, I know that if I take the antiderivative of f prime is going to rise up to the f level. And I can just do f of 2 minus f of 0. And I do f of 2 minus f of 0. That is within our ability because we have a table to work with. So f of 2 is 7 and f of 0 is 10. And then we can find 5 times 2 q, 5 times 8 is 40. So we get m of 2 is 37. Right. So first theorem says, sometimes you want to look at what we're given. If we had the f prime graph in front of us, then we can just read and just calculate the area under the f prime graph. We don't have the f prime graph, but we do have f of x available to us. So we have to rely on something else. We have to transform this. We have to find the antiderivative here. So first theorem says, I know that I can take my f prime and then antiderivative it, and it will turn into uppercase f or turn into f. And then I can plug in my upper bound minus my lower bound.
Okay.
Right. So f of b minus f of a.
Okay.
And part D says, is the function m defined increasing, decreasing, or neither? So anytime I want to find information about increasing, decreasing, that's referring to slope. And slope is referring to the first derivative. So I have to build my first derivative. So I want to find m prime of x. So here's my m of x equation. M prime, the first term is just power rule, so that's not bad. The second term, though, I gotta do a derivative on this function, which means that I need to apply second theorem here. So derivative of an integral, we know that these two operations will cancel each other out. I'm just left with f prime of x. So here's my derivative of m of x. So now that I have my m prime, I can replace every x with 2. And then let's see, f prime of 2. Do we know that value? We do, because we have our table to pull from. So we get 60 minus 8 is 52. And then since my slope is positive, I know that my function is increasing at x equals 2. Okay, so we're given the equation 6xy equals 2 plus y cubed. We want to start here and we want to show that the derivative is equal to this. So we're going to go through whatever derivative process from here. And the nice thing is they're telling us what the answer is. We just have to bridge the gap between our starting point and our ending point. So looking at 6xy equals 2 plus y cubed, to find the derivative, we should be able to recognize, okay, we definitely need to do implicit because we have multiple y's. So dy dx will pop up along the way. And then the 6xy, the fact that multiple variables are being multiplied together, we have to apply product rule as well. So we'll do product rule, and then implicit will show up along the way because our y variable is getting impacted. Right. So if they wanted to do that, they wouldn't have given you the function. They would have started with this and asked you to solve it. Right. So if they asked you to solve it, then here they're saying that basically, I wish they would have maybe said, find dy dx and show that dy dx equals, because sometimes students, they look at this, they feel like that's the starting point, but in fact, this is the starting point. Yeah, so the wording could have been more clear. All right, so we know we're going to start with product rule here. So f prime g plus fg prime. I'm going to lay out my product rule here and then just build out each of my derivatives. So 6x becomes 6, y stays, 6x stays, and then y's derivative is 1 dy dx. And then the right side, 2 becomes 0, y cubed becomes 3y squared dy dx. So now that we have our derivative, we can now work towards solving for dy dx. So I'm just adding and subtracting in a way that will get my dy dx by itself. So add, subtract, get that dy dx on the same side, factor the dy dx out. And then it's nice knowing what they want the prop that our dy dx to look like. So that tells us, whether we've gone far enough or not. So in this case, once we find dy dx, we see, okay, it doesn't quite look like this form yet. So it looks like we can do some factoring out. So I factored a 3 from numerator and denominator. I get negative 2y over 2x minus y squared. It's not quite looking, it's getting close, but it's not exactly the same. So remember that if your signs are off, you can always multiply the numerator and denominator by -1. And if you get a different version, it'll still be in the same thing. Okay, good so far. All right, part C. Find the coordinates on the point at which the line tangent to the curve is vertical. So, oh, sorry, B, thanks. Find the coordinates of a point on the curve at which the line tangent to the curve is horizontal, or explain why no such point exists. So, yeah, parts B and C is being able to understand where this is coming from. So whenever we talk about a line tangent to the curve is horizontal, that means we're getting a slope 0. So the way we get slope 0 is we set the numerator of our derivative equal to 0. So this problem is set up nicely in the sense that even if students mess up for part A and they have but they can still do parts B and C because they have a dy dx to work from. So I think they designed it that way where even if students couldn't do part A, they can still do parts B and C because they have a starting point from part A. And then part C says find a line tangent where to the curve is vertical. So this is where slope is undefined. So the way we find slope undefined, we're going to set the denominator of dy dx equal to 0 and then solve for x and y. Okay, so parts B and C, we're working off of the same derivative, but we're looking at different parts of the derivative. Okay, is that good? Okay, so first step is part B, tangent is horizontal. So we want to find where slope is 0. Slope is 0 comes from the numerator. So we're going to just focus on the numerator and set that equal to 0. Yeah. So my numerator is that 2y. So if I set 2y equal to 0, I get y equals 0. But the issue is if I try to replace 0 into the original equation, I'm going to get 0 equals 2 plus 0. So what that tells us is that even though I found a y equals 0, but this point doesn't exist on the original graph. So if something doesn't exist on the original graph, that means it's not. It's kind of like an extraneous solution. It's not a behavior that actually exists on this curve. So we tried it, but we were unable to locate a point that lives on the function on the graph.
So whenever you're doing this, you always want to check it back into the
Yeah, you got to check it back into the original. Yeah, the derivative will tell you where the point will tell you where to look. But we were right. We have to always confirm that that behavior is actually true on the original graph. Okay, so part B is inconclusive, and then part C, vertical tangent, we're going to set the denominator equal to 0. So y squared minus 2x equals 0. Now, this is a bit more challenging because if you set y squared minus 2x equals 0, you realize that you can't solve at this stage because y squared equals 2x, right? We can't solve for two variables. So we're gonna have to do a little bit of substitution. Okay, we know that the behavior that would have to be true would be where y squared equals 2x. Well, we can't find the point at this stage, but what we can do is we can still plug this into the original function and actually narrow it down to one variable and then solve for either x or y. So we're going to go down the path of least resistance, and I'm going to solve for x because I don't want to deal with square roots. So I'm going to divide both sides by 2, and I make it x equals 1/2 y squared. And if I have x equals 1/2 y squared, I can take that, insert into the original equation, and then I can solve for whatever variable I'm able to solve for. I'm able to solve for y. So replace x with 1/2 y squared, clean all that up, 3y cubed equals 2 plus y cubed. Divide, combine like terms, divide by 2, cube root both sides, y equals 1. So if y equals 1, I can plug that back into the original equation now. Now that I have my foot in the door, I have my one value for my variable, I can now go back and find the other value for my variable. So I'm able to find a full order pair. Order pair 1/2 1. So that tells me that there is a vertical tangent at this order pair 1/2 1. That's tough. That's a tough one.
You plugged it back in.
Yeah, I plugged that that 1 back into my original equation, and I solved my other variable.
Okay, but you don't have to check for the x.
No, I don't, because if I can find one variable, I can just plug in. I don't have to go back and
You
solve
know,
it.
there's-
I already know it exists.
Okay, yeah.
Okay. Hey, I had a test with you. You can put it in. Yeah. Okay, see that. How big one? Sure you get it. And then you get that one. Same thing. Okay, all right, sounds good. Thanks, yeah. But everything, yeah, next.